Let's see. So you know all that stuff we did with curve sketching? We were just doing a full analysis of a function. Where does it increase? Where does it decrease? Can we find a max or min? Concavity, blah, 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 blah. Like, what we're going to do now is just take that idea and just zero in on this. Can I find a maximum or a minimum? Whatever they might be asking us to find. These are all word problems, our favorite. So a lot of the work is going to be in identifying what it is they want us to find, coming up with an equation that models this problem that will kind of help us find the solution that we're after. And then because we're just looking for, they'll say find the maximum or find the minimum of some quantity, right? So if we can get a function that models that quantity in terms of a single independent variable, then if we're looking, we can just use what we already know about how we find maxima and minima. We're going to find a derivative, set it equal to 0 to find those critical values. And then we can use, either make a sign chart for the first derivative or check the concavity at that point to see if it is a maximum or a minimum. And that's basically kind of what's laid out in this procedure. Sometimes it helps to sketch a figure. Not always, kind of depending on what's going on. So we'll just do a few examples. This first one says that there's a farmer who wants to who plans to fence a rectangular pasture. So the river itself is going to be one of the boundaries, and then using actual fencing for the other 3 sides. And she wants to maximize the area given that she only has 600 meters of fencing. So some rectangles with the 600 meters will result in bigger or smaller areas, and we just want to find that maximum area that we can make. So, all right, what they're asking us to do is to maximize the area. And that's an area of a rectangle. Somebody give me an expression that will give me the area of that rectangle. X times y, right? That's our length times width. Great. Now, I have the function I want to maximize. I'm not yet ready to differentiate because I've got to express in terms of 2 variables. And what I really need is to write that as a function of a single independent variable. But they've given me another piece of information. They told me that there's 600 meters of fencing total, and that's going to help me write an equation that relates x and y together, independent of area at all, right? If there's 600 meters of fencing, what does that tell us? What equation can we write that reflects that fact? X plus 2y equals 600. Are there questions about how we got that equation? Great. Okay. So look, if x plus 2y is equal to 600, then x is 600 minus 2y. I'm choosing to solve this equation for x because it's simple, and I get an expression in terms of y that I can then substitute into this function. If I chose, I could also have gotten an expression for y in terms of x and substituted that in for y. Like, it doesn't matter. Either option will work. So I'm taking this equation, putting it in for that variable, making a substitution. So now, only as a function of y, I'm writing the area is 600 minus 2y times y. So now I have my function written with just a single independent variable. Yes, we absolutely can take the derivative at this point. I'm going to wait. I'm going to do one other thing because I want my work to be as easy as possible. So what could I do first to make that easier?
Distribute the y.
Yeah, right, because then I don't have to use the product rule. When the reason that we want to write this function with just one independent variable is because when we differentiate, we're going to be doing it with respect to this one variable that we have. We're not differentiating; these are not time rates of change anymore. So we're going to distribute the y. And now let's find the derivative. Let's find a prime, or dA dy. What do we get? 600 minus 4y. And we're trying to maximize the area. We're trying to maximize the area, and we just found the derivative of area. So how does the derivative help us find a maximum or a minimum value?
We look for when y is 0.
We don't look for when y is 0.
When a is 0. Whenever we have to have
When a prime is 0. Yeah. Good. So we're going to set the derivative equal to 0. We're going to find those critical values. And so that means that 600 minus 4y is equal to 0. That means that 4y has to be 600, right? And then divide. A nice linear equation here. It turns out we get just a single critical value, and that gives us 150. This would be meters. Now, there's only a single critical value, so we hope it's the one that results in a maximum area, right? We don't want to assume that. So we have a couple of options. We could either make a sign chart for a prime, or I'm gonna argue that I think it's easiest to look at the second derivative. What is a double prime? -4, right? It's constant. So can you tell me whether it's concave up or concave down when y is 150? What's that? Nope. Well, yeah, so by process of elimination. Somebody, who wants to support that answer?
It's negative with concave down, right?
Yeah, a curve, when the second derivative is negative, the curve is concave down there. This curve, the second derivative is constant at -4. This curve is always concave down, everywhere. So, always concave down, so certainly concave down when y is 150. So that means that y equals 150 gives a maximum. Right, concave down looks like this. So there's our maximum. Notice I didn't say y equals 150 is a maximum. I said it is a maximum. We're maximizing area. We're not maximizing y. In fact, if we were maximizing y, I think we'd have a pretty small area. That would, if we were maximizing y, we'd have like super tiny, like, right? Like there might be like the maximum for y would be like 300, and that would have a area of 0. So that draws attention to a really important feature of this. We found where the maximum occurs. They didn't ask us to find the value of y that maximizes area, though. They said find the maximum area. So what we want to do now is figure out what that maximum area is. We could either do that by plugging it into this equation here or this equation here. It wouldn't take long to figure out what x is. Right, 600 minus 2 times 150, that's 300 meters. So the maximum area is 300 times 150. $45,000 square meters. This is your maximum area.
Which equation did you plug the 150?
So I found the x dimension by using that equation here.
Yep.
And then I used length times width, like x times y, the first one.
Oh, I see.
But you could also just plug y into this one. But I just thought it just felt kind of simpler to, this I could do in my head, almost. I had to do the last multiplication on the calculator, but like this one I could do in my head. So. Sometimes these questions will say, you know, find the dimensions that maximize the area, and so then what you just want to give are x and y. Sometimes they say find the maximum possible area. We don't want to assume if we find a single critical value, hopefully that means it's the one we're looking for, but we don't want to assume that. If they said find the minimum area that we could enclose, we wouldn't find that by using this single critical value that we found. So we always want to make sure we include a check that that critical value does yield either the maximum or minimum that we're looking for. Questions before we move on?
So we were looking for a maximum there because we were maximizing the area?
Yeah. Okay. This next example says find the point on the parabola y equals x squared that is nearest the point 6, 3. So this point 6, 3 is fixed, right? This point x, y on the curve we imagine could be anywhere, right? But we're trying to find that one so that that distance is, if it's nearest that point, we want to minimize this distance, right? So it looks like that point should be right around here. If I slide it up, clearly that's a bigger distance. If I slide it down, that looks like a bigger distance. So this looks like it's in the ballpark of where that point ought to be. Definitely shouldn't be over here anywhere, right? And it's on the point y equals x squared. So I know that this is, in fact, the point x comma x squared, right? We want to minimize that distance. What do we need?
Distance formula?
Yeah, we could start there. What does that look like?
Y2 minus Y1 over X2 minus X1.
That's the slope.
Y minus Y1 equals
That's the point slope form of a line.
The square root of x2 minus x1 squared plus y2 minus y1 squared.
Yeah.
So
Yeah, that's Pythagoras, yep. So there's the distance formula, or you could start with Pythagoras, right? D squared is equal to this squared plus that squared. And in fact, that's what I'm going to do next, really. Well, let's see. why don't we plug in our stuff here? So I'll call this my x1, y1, and this will be my x2, y2. So when we plug this stuff in, we have the square root of x squared minus, x minus 6 squared plus x squared minus 3 squared, like that. But yeah, we could begin right off by differentiating. We've already got it expressed as a single variable, so like that's great. You could differentiate right away. I'm actually gonna square both sides first. I'm going to square both sides first to get rid of that radical. And I'm going to FOIL out those squares, those products. So
does it matter if we have it x minus 6 or 6 minus x?
no, as long as you're consistent. We should be consistent. I mean, here you're squaring the differences, so it will not make a difference in the end, even if you weren't consistent, but we should be consistent. Okay. So another way to ask your question is, does it matter if I call this one x1, y1, or this one x1, y1?
Yeah.
And it makes no difference at all. So if we square both sides, that'll get rid of the radical, and as I mentioned, I'm going to FOIL these out. So we have an x squared minus 12x plus 36 plus x to the fourth minus 6x squared plus 9. And so we have x to the fourth minus 5x squared minus 12x plus 45. There's d squared. How's that so far? We haven't done any calculus yet. I mean, we're thinking, our brain's in calculus mode, right? But we're doing a bunch of algebra to get ready. We want to find the derivative. We want to find d prime, which is the derivative of d with respect to x, always respecting whatever variable we're using in our function in this section, in these problems. So on the left side, if we're taking the derivative with respect to x, you know, that's a d squared. So we start with like 2d times d prime, or dd dx, if you like. On the other side, that's a polynomial. We don't even need the chain rule, so Aaron is psyched. What do we get for the derivative?
4x cubed minus 10x minus 12.
Mm-hmm. Now what we want is d prime, so I'm going to divide both sides by 2d. Now we're dividing by 2d, and you'll notice that each one of these coefficients is even. So I'm going to just cancel that factor of 2 with the common factor of 2 we have up top. If I do that, what are we left with up top? Yeah, great. We might be getting a little nervous because we've written d prime, but not as a function of a single variable, right? We have both x and d in there. Now there's two ways that we could address this. One way is simply to observe that, well, we do have d as a function of x, so we could kind of pop that in down here. But then we could also just realize we kind of don't care. Like seriously, d is a distance, so it's always positive, and that's important to note. But also, we're looking to see where d prime is 0, right? We're going to find critical values. When is a fraction 0? When the numerator is. So, like, who cares? This is some non-zero, always positive value down here. So I really only need to focus on what's going on up top. So d prime equals 0 means that 2x cubed minus 5x minus 6 equals 0. Now this is tricky because this is a cubic and not a quadratic. It's a cubic and there's not even a factor of x, that I could take out. Like sometimes that's a way to go about it. Sometimes we end up with equations where we don't have nice algebraic techniques to solve. And this is the type of equation where it is completely appropriate to say, you know what, I'm going to have the calculator help me solve this equation. Your calculator can find intercepts. We're looking for where that's equal to 0. And so one way we could do that is by plugging this expression, the 2x cubed minus 5x minus 6, into our calculator, or y equals editor. So I'm going to do that here. 2x cubed minus 5x minus 6. I'm going to look at this on the standard window, like minus 10 to 10 first, and if I need to zoom in, I can. All right, so here's one thing I notice. It's only 0 in one location. It's a cubic, so I know it's actually not going to turn around again, right? And I want to find that one location. And here's how your calculator does it. It makes you kind of give it a window in which to look for the answer. So what I want to do is find the intercept. Because I'm just looking for where it's equal to 0, I'm just going to find the intercept. So I hit second calc. So where it says trace, right below the screen, there's a button that says trace. And in blue or orange letters above it, it says calc. So I'm going to do second calc. Number 5 is intersect. Oh no, I could do intersect. if I graphed another one. I'm looking for the 0. So option 2 is 0. It wants a left bound. So this is what I mean when I say that it needs you to give it a window to look in. So I'm just using the arrows. This is set to trace on the function. I'm just going to hit enter anywhere to the left of where that I could see that 0 exists. And then it wants a right bound, so I'm just going to go to the other side. Hit enter again anywhere to the right of where that 0 exists. So I'm giving it a window to look inside. And then it wants you to guess. And as long as there's only one 0 in between those two bounds, you can always just hit enter there. You don't actually have to put anything in. And then it finds it. Look, down here below on the bottom of the screen, it says x equals 2, y equals 0. So there's the solution to that cubic, x equals 2. Now, there's a single critical value, and it'd be nice if we could just assume that that's what does the job for us, but we can't. But since we solved this by graphing, look at the graph, and can somebody tell me by looking at the graph how I know that x equals 2 gives a minimum? Keep in mind, while we just graphed the numerator of the derivative, the denominator is always positive, right? So that means it's not going to affect the sign. It's not going to flip the sign around of the derivative of d prime. If we look at the graph, what can you tell me about d prime for values that are less than 2?
They're all negative.
It's negative. D prime is negative. Yep. And for values that are greater than x equals 2, it's positive. I can tell that the derivative starts off around x equals 2. The derivative is first negative, and then it's positive. What does that mean?
It has to be a minimum.
Why a minimum?
Because it's going from negative slope to positive.
Negative slope to positive. So you're saying it goes from decreasing to increasing. That's precisely what a function does at a minimum. That's the point at which it changes from decreasing to increasing. So we get that, so we got a lot out of this graph. We solved it. We didn't have a nice algebraic way to solve, so we graphed it. Also, it kind of gave us a nice, impromptu sign chart that we didn't have to make ourselves. Yeah.
So why is the minimum not at the bottom of the curve there?
Right, why is it not here?
Exactly.
So that'd be the minimum of d prime, but not the minimum of d. Right, this is a graph of the derivative, not a graph of the function. So if we graph the function itself, actually, hold on one second. Let's see. If we graph the function itself, I'm gonna do that. I'm gonna on y equals on my y2, I'm gonna put square root, and then inside, x minus 6 squared plus x squared minus 3 squared. I'm going to graph this on the same set of axes, and I think what I'll do is, I'll graph it in the same window for now. Okay. So look, right here, where it crosses, does correspond to a dip, right? And this is the distance function. And we can see that dip, that's what we're looking for. The derivative helps us find it, because where this is 0, this goes from decreasing to increasing. The graph goes from decreasing to increasing. This blue graph describes the behavior of the red graph, whether it's decreasing or increasing, and maybe how quickly, right? How steeply, depending on the value of how far down or how far up that is. If I were looking for this place, I'd be looking for where the d prime is a minimum, not where d is a minimum. So they wanted us to find the y coordinate, or they want us to find the point, so we need to find the y coordinate. So if x is equal to 2, it's on the curve y equals x squared. So, that's pretty easy. And so that means that 2, 4 is the point on the parabola that is nearest the point 6, 3. Yeah.
Where did you get the 2D from? They have the 2D.
So,
drawn?
yeah, so we started here, and then we took the derivative.
Yeah.
So that's a d squared, which means we had to use the power rule.
Yeah.
And the power rule would say 2d times the derivative of d. So there's 2d times d prime. Other questions? Okay. You want to do another? Yeah, we're ready. Okay, so we want to find the dimensions of a 700 kiloliter cylindrical oil tank that has the smallest surface area. The figure that's provided leads me to believe that this will be an open top. I feel like oil tanks probably wouldn't have an open top. That seems, you know what, let's close that top. How about that? That seems unsafe, unwise to have an open top. Okay, we're closing it up. First, safety. Okay? Yeah, then math. Yeah. Okay, so what we know about this tank is that it is in the shape of a cylinder. Right? And we know it has a fixed volume, 700 kiloliters. They're nice enough to give us this equivalence of kiloliters 1 cubic meter because we're going to want to be able to write our surface area function in terms of these linear dimensions. So we know that the volume is 700 kiloliters. I'm going to just sort of write that out on the side. The volume is 700 kiloliters. Or maybe I'll just write 700 cubic meters. Now, what is it they want us to do?
On the surface area.
Minimum surface. So what are we doing?
Minimize.
We're going to minimize the surface area. Okay. All right. So how do I get, what's involved in this surface area here? 4 pi r squared is the surface area of a sphere. Okay. I disagree.
Is it the 1/3?
So 1/3 pi r squared h is the volume. So is the volume of a cone actually, though, not a cylinder. So pi r squared h. Pi r squared h is the volume of a cylinder. So I'll just write that over here. That'll be useful. There's an equation, by the way, that this equation relates r and h together, and we will find that useful. But let's just sort of physically break this down. If I want the surface area, the area all around, first of all, I got a base and a top. They're both a circle. So I got 2 pi r squared for those. And then I need the area all around. This isn't a formula you need to memorize or anything, but like if I imagine my cylinder without a top or a bottom, so this is what it looks like, right? And I want the area all the way around it, imagine that I can cut it up the side and roll it out. And when I do that, I realize, oh, it's just a rectangle. I know how to find the area of a rectangle, length times width. So one of these dimensions is just the height of the cylinder, right? This other dimension is that circumference around the top, around the circle that forms the top and bottom base. And the circumference is 2 pi r. So that the area around it, what we call the lateral surface area, is 2 pi r h. There's your like length times width of that rectangle that we got when we unrolled it. Not a formula you need to memorize. So don't sweat that. But we have our function that gives the surface area. We know that we want to minimize it. Can somebody explain to me why I'm not ready just yet to differentiate? Yeah.
Well, I mean, so the answer to your thing is because we have two different variables. But I have a question.
Yes.
Why is the first chunk of that surface area equation 2 pi r squared?
So I have a pi r squared on the bottom and a pi r squared on top.
Oh.
So I got two of them all together.
Okay.
Yeah.
No,
Safety.
That's fair.
It's for safety.
I was thinking 2 pi r instead of. Yeah. Okay. Cool.
So we need this function written in terms of a single independent variable before we're ready to differentiate, and that's where this guy's going to come in handy. This volume, right? So there's in these problems, they tell you what you want to maximize or minimize, and then hopefully they either give you a function or we have enough information to find that function. But then, unless that function is already written in terms of a single variable, like unless it's automatically given in terms of a single variable, they'll always give you another piece of information, like a constraint, because if the volume weren't limited to 700 kiloliters, if the volume didn't have to be 700 kiloliters, I'd say, yeah, minimize the surface area, just make it super small, right? That'd be a silly way to minimize the surface area. But we know that the volume is 700 kiloliters. So I'm going to, now I could either find R in terms of H, or I could find H in terms of R. I'm going to find H in terms of R, and there's two reasons. One is that if I find H in terms of R, there's only one spot that I need to substitute it in, and that's kind of convenient. The other is that it is just simpler to solve that equation for H, right? All I have to do is divide by pi r squared. So H is 700 divided by pi r squared. Simple. So now I'm going to rewrite this function. Still not differentiating. I'm getting myself ready to do that. So 2 pi r times 700 over pi r squared. I can simplify. An ounce of algebra is worth a pound of calculus. All right, I want to avoid things like the product or quotient rule if possible. Not that they're not enjoyable, but I don't have to make extra work for myself. So those pi's cancel. One of these factors of r cancels. And we have 2 pi r squared plus 1400. And I've got 1400 over r, but I'm going to take the derivative. So I'm actually going to write that as 1400 r to the minus 1. Why is that nicer? Yeah, right? That's just a product rule. Because 1400 over r, right, since the top just didn't have any variables, it's legit easier to just rewrite that. It's 1400 r to the minus 1. Now taking the derivative is, fairly simple. If I take the derivative, I've got a prime on the left. What do we have on the right? Four pi r yeah. So once I have the derivative, how does that help me? I always like to start out these problems. I write out what my goal is. I'm minimizing or maximizing, whatever, this function. So I want to keep my eye on the ball. How does finding the derivative help me accomplish that goal? Yep, so what do I want to do? Yeah. So a prime equals 0 means that, now I'm going to set this expression equal to 0. When I do that, I'm actually going to rewrite that second term back in the form of a fraction. So we get 4 pi r minus 1400 over r squared equals 0. There's more than one way that we could kind of go about this algebraically. They're more or less equivalent. I'm going to just throw that fraction on the other side. So we'll have 4 pi r equals 1400 over r squared. We're solving an equation with fractions, so what should we do? What can we do that's particularly useful? Yeah, we want to clear these denominators. So times r squared, and then we get 4 pi r cubed equals 1400. And we're going to solve this for r, but I guess, we'll go ahead and find r cubed first. Divide by 4 pi. 1400 over 4 is 350. So 350 over pi is r cubed, which means that r is the cube root of 350 over pi. What did the problem ask us to do?
Find the dimension.
Yeah.
So that would just be.
So here's one of the dimensions. We're not quite done with r just now, and I'm not going to go ahead and find h yet, because what if this doesn't minimize it? What if in some way maybe that actually gives me a maximum, right? I want to make sure I can verify that that's the minimum before I go ahead and right? So what could I do?
A double prime, we check to see if it's positive.
Yeah, right. For minimizing, if we use the second derivative, we want to check the concavity at this point. If it's concave up at this value, then we've found our minimum. So hold on. I'm gonna, for ease of evaluation, I'm gonna just 4.81 meters. So we're going to verify that this gives a minimum. So here's our A prime is equal to 4 pi r minus 1400 r to the minus 2. So what is a double prime?
4 pi plus 2800 r to the negative 3.
And we're going to evaluate this. I'm going to simplify first. I'll call this, or just rewrite as in the fraction form. I find it convenient over r cubed. So you said we want to make sure that the second derivative is positive, right? If it's concave up, then we found our minimum. There's not a whole lot to do here. If I plug in 4.81, I mean, we could plug it in to the calculator and see that we get a positive number. But can somebody look at just how this, look at this expression. Can you explain why I know this is going to give me a positive number?
It's 4.
Because it's a cube
No.
root.
Constant plus or something.
Constant plus a what something?
It's ours.
A positive something, right? If I plug in a positive, r cubed is positive, right? So this will be positive always, and we're adding positive 4 pi. So yeah, this is definitely positive. And that means that we have a minimum. So now we'll go ahead and find h. We already have expressed h as a function of r up here. We did that so that we could plug it into the function, but we'll just go ahead and use it again. 700 over pi r squared, so 700 over pi times, let's see, 350 r squared. Since r was that cube root, that means that when we square it, we'll have the 2/3 power. Oops. 9.62 meters. So these are the dimensions that we're looking for.